It turns out that exponential growth and decay, or how we keep up with changes in populations, is overtly itself usually not directly tested on the BC exam, but it leads into our discussion of logistic growth models. And so it's something that I still continue to cover, and we'll do some homework problems over it, but it's just a lead in to the logistic growth stuff that we're going to do after we get through with slope fields and Euler's method and such. So exponential growth and decay is something that you worked with already. You've probably worked with it in Algebra 2 and in Pre-Cal. So let me just kind of remind you of some things, and then we'll just do one example, and we ought to be able to get through this in one video. So exponential growth and decay usually deals with populations. Now, we're used to dealing with populations of humans, rabbits, bears, wolves, whatever, bacteria, but it could also be a population of radioactive material or whatever. So when I say populations, it's a very loose definition of populations. So let's specifically talk about, first of all, the world's population and kind of get an idea of how that's handled mathematically, because it's a good example of exponential growth. So the growth of the world's population has been a mathematical question and model forever. Historically, mathematicians have handled the question by looking at sample populations from the past to get an idea of what might happen in the future. And it was determined by this method that populations, human or otherwise, as long as it's of something alive, populations grow at a rate proportional to the size of the current population. This is always true. So when we have any population that's growing at a rate proportional to the size of the current population, we're talking about exponential growth. Or if the population is in decline, we're talking about exponential decay. And if that's the case, then we can use our knowledge now of differential equations, and we can come up with a function that models that behavior. So at the beginning of 1987, the world's population was about 5 billion. It was mathematically determined that by the year 2010, the world's population would reach 7.7 billion. Was this a reasonable assumption? As it turns out, it was reasonable. It was a little high, but it was reasonable. Mathematically, it was approached by letting y equal f of t be a function that denoted the size of the world's population at any time t. We have to model things mathematically, where t was the number of years after 1987. So in 1987, t was 0. So we started with a base, an initial population. Y naught is usually initial population of 5 billion. So since the graph of this function is a discrete model, and by discrete it means, we're counting individual things. The data in this collection is finite pieces of things. It's human beings, wolves, bears, mice, even bacteria are individual finite data pieces that we are going to model with a continuous mathematics. So we have to keep that in mind. So this says, since the graph of f of t is a discrete model, we're assuming the jumps in its graph when someone is born or dies will be small relative to the total population that we feel confident in approaching this problem using the calculus of differential functions. Now, calculus is a continuous mathematics. It doesn't really take into account the fact that, we have finite individuals in our population. So we are going to have to understand that we are using a continuous mathematics to approximate discrete data. So we have to remember, if our mathematical result is a part of a whole, we don't have 2/3 of a human being or 5/10 of a bacteria. We have a whole human being or a whole bacteria. So we may need to adjust the mathematical model that we're using, which is a continuous model. We may have to adjust our final answers to make it make sense in the context of our question that we're being asked. All right, so here's the relationship between initial population and time. We can suppose that the increase in population, that's births minus deaths, and we've assigned that y, this is the population, the current population, during a short time period, t, is proportional or varies directly, that's where this little k comes from. If something varies directly, then we have a constant of proportionality to the size of the population at the beginning of the period and to the length of that period. So this says, in mathematics, the change in the population over time, the rate at which the population is changing, is a proportion of the current population. So everything we said in words on the last slide is right here in mathematics. And now we know how to separate and integrate. This is a differential equation. If we want to start with the differential equation and get back to the original equation, we are going to separate and integrate. So if little k is positive, the population is growing. If little k is negative, the population is shrinking or in decline. That's not new information to us. When we worked with exponential growth and decay back in Algebra 2 and pre-calculus, we knew that. If k was positive, the population was growing. If it was negative, the population was in decline. So historically, mathematicians assign the value of 0.019 for modeling the world population in human beings. There is some argument that it's too high, but this has been accepted traditionally. We want to solve the above differential equation, this one, this whole dy dt equals k times y, under the conditions that we're looking at an initial population and an initial time. So we want to separate everything to do with y and dy on one side, everything to do with t and dt on the other. We can just leave our constant over here on the right-hand side of the equal sign. No need to keep it with the y. So we're going to separate, and then we're going to integrate. And so again, here on the left-hand side, hopefully you can see that's 1 over y dy. So this is the derivative for the natural log function. So the antiderivative is going to look like this. So on the left-hand side, we have the natural log of y. What did we take the derivative of with respect to t to get k for an answer? That was k times t. We have to remember to put our plus c. It turns out that our plus c, given the condition that the current population and the initial population are equal at time t equals 0, then we know that c is going to wind up being algebraically the natural log of the initial population. So we could do this another way as well. We'll see this on the next slide. I want the general solution. So I'm going to raise both sides to the power of e right here. So I wind up with y on the left-hand side and e to the k times t plus c. All that's been fed into the e function machine on the right-hand side. So we want to go ahead and I want to show why this is the natural log of the initial condition. I'm calling this c. Realize that if I have e to the kt plus c, that this plus says that I have the equivalent of e to the kt times e to the c. Well, the result of this is just a constant. So what I have on the right-hand side of the equal sign here is I have e to the kt times c. And I can just, I put c out front, e to the kt. And it turns out that this is the initial population. All right, so y equals y naught e to the kt is the formula that I'm going to use for any population. Any population that is growing at a rate proportional to the current population, this is an excellent model for that population at any time t. All right, so let's go back to what they said. In 2010, remember at t equals 0, we're in 1987. So in 2010, we're at t equal 23. We said our initial population in 1987 was 5 billion. So if we plug those values in for y naught and for t, and world population grows roughly at the rate 0.019, it turns out that the world population in 2010 should have been 7.7 billion. And actually, it was roughly 7 billion. So, you know, it just depends, I guess, on your idea of what's accurate and what's not. I mean, we were off by 0.7 billion, by almost a billion individuals. So is it reasonable? Yeah, it's reasonable. We were in the ballpark, but it, you know, still wasn't great. All right, so the difference between growth and decay, remember, is this value of k. If we are in decay, k is going to be a negative value. You don't have to force k to be negative. It will turn out to be negative all on its own. All right, so we've used the growth of the world's population to explore exponential growth, but not everything grows. Some populations and materials decline. Radioactive decay contains elements that decay over time. It is true that we use the same exponential model for these types of situations, and this is the case where k is going to be negative. Since radioactive decay is most often referred to in terms of half-life, not always, but most often, I'm just giving you this information just in case you are given half-life information. Well, understand half-life tells you that after so many years, half of the population is gone. So the relationship between y and y naught is that the current population is going to be half of the initial population if we have half-life going on. So that's why you've seen I have replaced y with 1/2 and y naught with 1. So when we're dealing with half-life right here, this is the model that we can use. So generally in these types of problems, you'll be given an initial set of data to determine the value of k. Then you're going to use that value of k to answer the final question concerning rate of decay. So let's do our one example here. I think we can get through it in time before the end of the video. Carbon-14, one of 3 isotopes of carbon, is radioactive and decays at a rate proportional to the amount present. So that tells me here we are in this exponential model. Its half-life, so now I am in this model, because y naught is 1. Its half-life is 5,730 years. That is, it takes that long for a given amount of carbon-14 to decay to 1/2 its original size. If 10 grams were present originally, how much will be left after 2,000 years? All right, so we have some players here. We're going to have to find k, and then we're going to have to find y. So this information will help us find k. The half-life is 5,730 years. That's how we're going to find k. So I'm going to take the natural log of both sides. So 5,730k. So little k is the natural log of 1/2 over 5,730. And you say, well, that's supposed to be negative. Well, it turns out that natural log of 1/2 is a negative value. And I'm purposefully not giving decimal approximations because I want you to know that this can be done without your calculator. That's a real number value. It's a very valid real number value. So now I have some decisions here. It's asking for y, right? What is the population, what's left after 2,000 years? So I want y equals y naught e. I know what k is. It's the natural log of 1/2 over 5730. And t is 2,000. So there it is right there. That's how much is left. And I don't need a calculator to get a decimal approximation. That's a real number value, and that's an answer. That's how many grams will be left after 2,000 years. So like I said, they're going to give you some information that helps you find the value of k. Then you're going to use that value of k to actually answer the question that they give you. So there we are. There's the lesson on exponential growth and decay. So come next time and we'll do some homework problems.